Thank you.
I'm sure it will be.
Bienvenidos al Laboratorio Internacional de Partículas Elementales de la Universidad de Guanajuato. Lo fundamos el año 2005 para estudiar las partículas elementales y desarrollar tecnología de detección de radiación, incluyendo rayos cósmicos. Hemos atendido a más de 100 estudiantes de servicio social, 30 estudiantes de licenciatura, 20 estudiantes de maestría y 10 estudiantes de doctorado. Desarrollamos investigación en tecnologías de detección de radiación. Hemos logrado algunas innovaciones que han merecido premios nacionales e internacionales. Colaboramos en experimentos internacionales de primer nivel. Hemos creado el seminario Leo Lederman, difundido internacionalmente a través de medios digitales. Ha llegado a más de 1 millón de personas, especialmente jóvenes de Latinoamérica, en 6 meses. Contamos con invitados internacionales expertos, líderes en su área, de primera línea, que exploran las fronteras de la ciencia. Let me introduce your seminar in Spanish.
That's okay. Pleasure.
Saludos y agradecimientos desde la Universidad de Guanajuato, en colaboración con el programa STEAM de la Universidad de San Carlos de Guatemala. Gracias a todos los estudiantes y el público en general que atienden este seminario de casi todas las Américas. Desde Argentina, Chile, Perú, Colombia, Uruguay, Guatemala, Salvador, México y otros países. También sabemos que nos siguen de España, de Alemania, de Estados Unidos y de otros países de no habla hispana. En este seminario tenemos como invitado al profesor Francis Halzen. Halzen es físico de partículas. Él es profesor distinguido de la Universidad de Wisconsin en Madison y director de su Instituto para la Física de Partículas Elementales. Halzen es el principal investigador de IceCube Neutrino Observatory en la estación Amundsen Scotch del Polo Sur en la Antártida, el detector más grande de neutrinos en operación desde el 2010. Francis Halzen habla en este seminario para ustedes IceCube, Recent Developments, en español es IceCube, desarrollos recientes. Agradeceremos también sus preguntas por chat. Disfruten esta interesante charla. Les dejo con el profesor Francis Halzen. Gracias, Francis. Bienvenido. Thanks you, Francis. You are welcome.
It's a pleasure to be here. Thank you for the invitation. So I am ready to go. Shall I share my screen? Is this okay?
Yes, we can see it.
You can see it?
Yes.
All right. So, but mine doesn't move. Let's see. There is.
It's on presenter mode. If you go to the three dots behind
It's
the
presenter
below the
mode,
slide.
yeah. Should I get out of presenter mode? Let me use slideshow. Is that better?
Yes.
Oh,
A
okay.
full screen.
Yeah. All right. I'm ready to go. So I'm going to tell you about the South Pole Telescope and what we did with it in the last decade of taking data. And actually, as was mentioned, I gave a talk before, and my outline is the same as my previous talk, except almost all the slides are different because I'm going to emphasize different things. And I hope that the talk does not become more technical. But at the end, I think what will be interesting is we have a lot of new results that we obtained since my last talk, Letterman lecture, and I will spend time presenting those. So I'll go to the menu I just showed you, and I have to explain to you what a neutrino is before I can tell you what neutrino astronomy is. And I will let John Updike introduce the neutrino. Everybody used to do this in the neutrino talks, including me, but since he died a few years ago, we stopped showing this beautiful poem. And John Updike says neutrinos, they are very small. They have no charge. He means no electric charge. That's very important. They have no mass. That's not quite true, but in this talk, it's true. I mean, in this talk, neutrinos are like photons, like light. The particles have no mass. They do not interact at all. That's almost true, but it's not totally true. Otherwise, I wouldn't be giving this talk. And then he said, the Earth is just a silly ball to them, through which they simply pass. And that will also be important in this talk, as you will see later. This is an incredible introduction to neutrinos. Here is my introduction to neutrinos. The neutrino was basically discovered in this experiment by Halzen and Mott, who were working for James Chadwick at the University of Cambridge in the 1930s. And they were kind of doing the first nuclear physics studies. And the neutron can fall apart into an electron, a proton, and a neutrino. And you say, what? Why not just a neutron falling apart in a proton and an electron? Well, they noticed when they measured the decay of the neutron that when it fell apart, the electron and the proton would occasionally take off in one direction, like to the left of my screen, and that violates energy and momentum conservation. So there must be a particle which they actually didn't detect. They only see its energy and momentum. And they could actually measure that its mass is very small. So was it a real particle or not? They didn't know. They called it a ghost particle. But by today's standards, this is what we call a missing energy, a missing mass experiment. And Halzen and Mott discovered the neutrino. It was rediscovered in 1956 by Reines. Now, this is a bit of a painful slide. This is the worst slide in the talk, but so hang on, and it will pay off. It will be useful later. So I already explained this. Changing neutrons to protons, that's nuclear physics. And it's only made possible because of the neutrino. The neutrino is somehow there to make this reaction that changes neutrons into protons possible. So you can think of the neutrino as this ghost-like agent that is present wherever there is nuclear physics. And how do you observe the neutrino? At Cambridge, they couldn't. They only saw its energy and momentum. Well, what you can do is you can have a neutrino interact with a proton or with a nucleus, like the proton is the nucleus of hydrogen, yeah, right? And there's a lot of hydrogen in the ice. It's frozen H2O. Come back to that later. And when a neutrino hits a proton head-on, it makes a positron, an electron with positive charge, and a neutron. And this is very important because now the neutrino which has changed itself into a particle which has an electric charge. And particles without electric charge are hard to see, as I explained. But once they reappear with electric charge, it's easy. You send the particle through a clear medium and it emits blue light. I will explain this later. But fortunately, there is also another neutrino, which is called a muon neutrino. There are 3 of them. And when it does the same thing, it produces a muon, which is like a heavy electron, and it's also charged. And it makes blue light in your detector. So this allows us, so the neutrino reveals itself by changing itself into electrons and muons when it interacts with a nucleus. So neutrinos are everywhere where there's nuclear physics. I showed this slide the last time, the Big Bang. When stars explode, there is a nuclear reactor in the sun that makes neutrinos. They make neutrinos at Fermilab. Our body emits neutrinos, quite a lot of them actually. And you see here this picture. That is a picture of a nuclear reactor covered with water. And you see the particles coming out of the nuclear reactor make blue light. For the physicists, this is called Cherenkov radiation. So another place where there are neutrinos are in the atmosphere. Because there are particles called cosmic rays, they are mostly protons. They enter from all over the universe. They enter the atmosphere and they hit the nitrogen and oxygen. And then they make a particle which is called a pion, and this pion makes muons and neutrinos. Actually, both of the electron and the muon type that I introduced. So the reason I showed this is if you look up at the sky and you look for neutrinos, you see lots of them. They are produced by cosmic rays hitting the atmosphere. And they will be a problem because they are not neutrinos that we are interested in. They are a background. They are like clouds that are hanging over our heads, except they never go away. But there is something else that I have to mention that's interesting. That is that that to make neutrinos, neutrinos are made from the decay of particles like pions, and you produce them with protons. So that means wherever there are neutrinos, and also here, there's nuclear physics going on. So it means when you look at neutrinos coming from the sky, you also look at places where the protons accelerated. Without accelerating protons, you can not make neutrino beams. It's the same at Fermilab, they accelerate protons to make neutrino beams. So why neutrino astronomy? I already mentioned neutrinos, they have no mass, they are particles, actually there are more neutrinos than protons neutrons and electrons in the universe. And so there are lots of them in the sky. And so they have no mass, so they're just like particles of light, like photons. So in fact, the idea that to do neutrino astronomy goes back as soon as Reines rediscovered the neutrino in 1956. And so what you want to do is you can use neutrinos and make a picture of a sky. This is the picture of the sky that you make with your eyes. You see here the stars in our galaxy, the sources of light that are nearby. And then in the background, you see the rest of the universe. This is the plane of our own galaxy, and you see their sources of light. I showed this to remind you that this was the projection I will use. So when I show you the universe later in neutrinos, you will look at this picture, but at neutrinos instead of light. Now, this is the picture I just showed. Now you can look at the sky in all kinds of colors of light, like in X-rays, in gamma rays, in microwaves, and look, the sky looks totally different. So this is an interesting game. When you look at the sky in a different way, you learn and see different things. And what's little known is that this doesn't go on forever. When you come to high energy gamma rays or very short wavelength, the sky suddenly turns dark. And the rest of the universe we have never seen. So it's like the dark side of the moon. And so the idea was that here, if we could detect neutrinos, we could do astronomy with neutrinos. And is there something interesting in this dark side of the sky? Well, there are cosmic rays. And so let me first explain why the sky turns dark. It's very simple. Suppose a galaxy far away emits light. That light, to make it to our telescope on Earth, has to travel through the microwave background. What is that? Well, you know, in the whole universe, there are 411 photons per cubic centimeter everywhere. So it's inevitable that this photon eventually will meet one of these 411 per cubic centimeter. And what it does, it transforms itself into an electron-positron pair. And then it has become charged particles. And that's a problem because charged particles are bent in the magnetic field. In the magnetic field outside our galaxy, it will enter our galaxy, be more bent by the galactic magnetic field, could get bent by the Earth magnetic field. And so it doesn't know where it comes from. For instance, if this accelerator was a cosmic ray source, this galaxy here, it would emit protons, but these protons would just swirl through the magnetic fields to our detectors, like they do at Auger in Argentina. But they don't remember their direction where they come from, so you cannot really do astronomy, or it's very, very challenging. So you want a particle that makes it through the microwave background that doesn't interact very much, and you want it to be electrically neutral so that it's not bent by magnetic fields, and that's a neutrino. And so neutrinos have no trouble penetrating from the edge of time, from the beginning of the universe. They reach the detector. And so that was the idea, to do astronomy with neutrinos. It's an obvious idea, it's a good idea, it's yet another way of looking at the sky. And if we look at the sky in this extreme universe that we have never seen before. And I always show this, the next slide. Why I personally am doing this is that I'm a particle physicist, that you heard in the introduction. But I remember when in 1991, I heard about this modest experiment in Utah that discovered a proton that had an energy of 300 million TeV. Now, you remember, the Large Hadron Collider in Geneva can reach an energy of 14 TeV. The Tevatron at Fermilab reaches energies of 1 TeV. When you are a particle physicist, how can you not spend the rest of your life figuring out where and how this happened? Remember, the cosmic rays themselves don't tell us where they come from. But if we can catch neutrinos that are associated with these cosmic ray accelerators, then we will know where they are located and how they accelerate particles. By the way, if you think of these neutrinos, these protons in terms of astronomy, they have a wavelength of 10 to the minus 16 angstrom. Oh, and suppose I use LHC magnets to accelerate that particle. Well, you have to fill the orbit of Mercury to do that. And I don't think this is how nature does it. So we have to build a big neutrino detector. And in fact, the theorists anticipated, it took a couple of decades for the theorists to try to figure out how big a telescope you needed. And you needed a telescope that's like a square kilometer mirror. The problem is you don't detect neutrinos with a mirror. And but we know how to catch the neutrinos in other ways. And so this is a neutrino experiment in Japan. And you can see here what you need is water and photomultipliers. Photomultipliers are these things. They are huge light bulbs, 20 inches. And instead of emitting light, they detect light. So you need water and light detectors, which you call photomultipliers. The problem with this beautiful experiment is that, again, according to the calculations, if we are lucky, it's still 10,000 times too small to do astronomy. So how do you solve this problem? This seems hopeless. Well, the answer came from Markov in 1960. And rather than telling you what he said, I will show you a cartoon of what he said. And so what you do is, let me go back and remind you, neutrinos come through the Earth. So if you look for particles through the Earth, you only see neutrinos. That solves the problem of selecting the neutrinos. Then I told you when a neutrino hits a proton, like a hydrogen in the ice, then it will make a charged particle called the muon, and charged particles in a clear medium like water, which was the suggestion of Markov, will emit blue light. And it would emit this blue light in this triangle shape, which is called the Cherenkov cone. So all you need are, again, light sensors, and you fill a kilometer cube of water deep in the ocean with light sensors. And then you can map the Cherenkov cone, and you know where the muon and the neutrino came from. So you have a telescope, you know the direction, and the neutrino points right back at its source. Here is a photomultipliers we will use eventually. They are 10 inches and they are a simple device you buy in Japan, and they detect blue light. And so the reason you have a telescope, I have to comment on first. This muon travels like 50 meters to 50 kilometers through the ice. So even if it is a hydrogen nucleus outside your detector, you can still see the muon go through your detector. And it goes close to the speed of light because we are working at very high energies. Remember, typical energies in this talk are 1000 TeV. And the speed of light in water is 3/4 of the speed of light. So the way to think about this is like this duck. You know which direction it's moving because the waves in the water are traveling slower than the duck itself, and so it makes a bow wave, a shock wave. And so we just see the neutrinos doing that by emitting blue light in the water and reconstructing, make possible the reconstruction of the direction of this neutrino. So it's all well-established simple physics. So a kilometer cube detector can look like this. You see each of these dots, which you have difficulty seeing, are one of these 10-inch photomultipliers. And you see here, this is a real event. This is a neutrino. It comes through the Earth 11 degrees below the horizon. It interacts with a proton, makes a muon, and the muon speeds through the detector at the speed of light and lights up all the light sensors. And if you look at this, by the way, the color from red to green, following the rainbow, tells you the direction. If you didn't get it yet, here is the movie. You see the neutrino coming in, the muon coming in from the left and going through the detector. By the way, you can by eye, you can see the direction of the muon in this event display. As I said, the idea went back to the 1960s, but it took quite some time until an experiment was developed, which was called DUMANT, that tried to do this off the coast of Hawaii. And unfortunately, it was discontinued in '87. It failed. It's very difficult to deploy sophisticated technology in the ocean and make it operate. This problem has been solved now, but we at that time had the idea of doing something simpler. Why not melt the photomultipliers into ice? And then if the ice is as clear as the water, we are in business. Because we anticipated that melting light sensors in ice would be easier than deploy them in the water. And you can imagine that was a hard idea to sell, but it turned out, we know now it turned out to be true. So where do you find ice? You find ice in Antarctica. And so the idea is you build a detector in Madison, Wisconsin. It goes by boat or by plane to Christchurch, New Zealand. Actually, this building is at the airport in Christchurch, New Zealand. And from there, by plane, all your stuff goes to McMurdo Base, which is like an Alaskan boomtown on the edge of Antarctica. And then it's another 3-hour flight to the pole. So this is quite a journey. But if you arrive at the pole, this is what you see. And the important thing is here that you stand on 3 kilometers of ice. And the other important thing is, if you look in the other direction, you see the National Science Foundation and a NSF station. So you have an infrastructure, it's a research station that allows you to deploy and set up rather challenging experiment. And the other thing is, if you go there at night, it's still there, it works, it's open at night, so you have year-round people can be deployed there to babysit the experiment. So here is again an image of Antarctica. The South Pole is here, and you see here where my arrow is. There you have 3 kilometers of ice. And we studied this ice for about 10 years and discovered that it's fantastically clear. In fact, the blue light travels through this ice for 100 to 300 meters, depending on the depth. And so once you are below 1.5 kilometers, you have lots of space to deploy light sensors, just like the DUMANT experiment did in the ocean. By the way, this was a purely serendipitous discovery that this ice was so clear. In fact, it's the clearest solid in nature, and you cannot even produce it that clear in the lab. And the reason is this is 50,000-year-old snow. It fell on Antarctica 50,000 years ago. It's totally pure and has been compacted. And so we found the ideal medium to build this detector. So all you have to do is melt it in the snow. And there was some discussion about this. And I want to do away with the question, how do you melt photomultipliers by showing you a movie. So here you see a picture of the South Pole. This is where my arrow is. This is the South Pole station. Here you see the South Pole, and here you see the IceCube construction site. This is the runway where the planes land. And we built a small detector called Amanda, and that's the detector that revealed to us this clear optics, and that allowed us to move to a bigger experiment. In fact, I remember the day I saw this event. This is a neutrino detected by this small instrument, and it showed that we could actually, that the method worked. This was very exciting. So we built IceCube, just more photomultipliers, fill the kilometer cube of ice, as the theorists told us to do. And you see here, if you could go in the detector, you will be here 1.4 kilometer deep. Sorry, no, not yet. 1.4 kilometer deep and a kilometer long string, and every 17 meters, this 10-inch light bulb. And you go 125 meters away, there's another one. And so 86 of these strings of light sensors fill the kilometer cube of ice. So if we zoom in on the light sensor, you will see what they are. You see the light bulb, 10-inch light bulb at the bottom, and at the top, it's just electronics. And the electronics transforms the light in a digital form that's sent to computers at the surface. Simple experiment. And so here is a picture, 1.4 kilometers under the surface, 5,160 light sensors filling 1 kilometer cube. So here is how you melt them into the ice. The top 800 meters or so is snow, so you just melt your way through it. Then comes what's called the hot water drill, and the hot water drill is just a nozzle that puts out boiling water under pressure. And it falls by gravity, and after 2 days, you have transformed a pipe, a long hole of ice into water. Then you pull it out. In fact, this hot water drill delivers 200 gallons of boiling water per minute. And so this requires about 4.8 megawatt power plant. And so the whole drill is built on sleds. So it's like a circus train, but it's on sleds which move over the ice. This is a hose that brings down the hot water. It's 2.5 kilometers long. This is the 4.8 megawatt heating plant driven by normal fuel. They are like 40 car wash heaters. They are a bit souped up, but that's basically what they are. And so after 2 days, you see here the drill comes out. You will see the drill head in a minute. This is the nozzle that puts out the hot water. And you see, then you move further and you deploy another string. 86 strings are IceCube. But remember, ice is an insulator, so that water remains liquid for some time, like for a day. And so during that day, before it refreezes again, you put in the sensors you lower the cable brings down the electricity to the center, and the cable brings up the digital signals telling you about the light that the photomultipliers, that the light sensors detect. So in principle, it's simple. And the beauty of this is it's now a proven deployment technology. The team did this 86 times without failing, and it delivered a detector that was totally stable. Nothing happens to it. It just sends back digital data to the place where I'm sitting here in Madison over satellite, and it has been doing this through COVID, and it does this with an on-time of more than 98, typically 99 point something % of the time. So here is a picture during the polar Antarctic summer, December, January of that year. 20 of these strings were deployed, and you see their data goes into this 2-story building, and this 2-story building is filled with computers that reconstruct the patterns, like the pattern, the Cherenkov pattern of the muon that I showed on my earlier cartoons. So what do you see when you turn IceCube on? Well, remember this picture? You look up at the sky, you detect neutrinos. In the atmosphere emits neutrinos. Well, that's what you see. Because, sorry, let me make clear, the neutrinos made in the atmosphere all over the Earth, eventually some of them can end up in your detector at the South Pole. This detector is at the North Pole. This is the South Pole for us. So remember, when we look through the Earth, we see the sky above Madison and above South America. But what we see, unfortunately, are these muons and neutrinos that are made by protons hitting the atmosphere. And so we see actually 3,000 muons per second going through IceCube, and we detect 1 neutrino every minute while I'm sitting here. So 100 billion muons per year, 100,000 neutrinos, which are interesting, but not for this talk. But this is the background in which to have to find cosmic neutrinos. And so we were taking data, and after about 2 years, someone accidentally, we were looking for something else actually, accidentally found this event. And this event is, you see no muon track, right? You only see, you see this ball of light. Well, this is an electron neutrino. So an electron came in, an electron neutrino came in, made an electron, and the electron made a shower of particles in the ice, and this, what you are looking at, is the radiation from this shower. So this shower is only like 7 meters long in this case, and so it's like someone turns on a light bulb in your detector. But the interesting thing about this is we see all the light now inside the detector, so we know exactly what the energy of this neutrino is. And the energy of this neutrino is so high that it's very unlikely to be produced in the atmosphere. The atmosphere makes lots of neutrinos, 1 in every 5 minutes, but few of them have this energy. In fact, it's very unlikely that any of them have this energy. But you know, we saw 2 events like that by accident. So what did we do? We went and looked again through our 2 years of data, specifically looking for balls of light like this. And you see what you are looking at here is the other case that I mentioned. An electron neutrino makes a positron. This positron will make an electromagnetic shower, and all the charged particles radiate light. And so we know all the physics, how this happened, so we can reconstruct the energy of the neutrino. And you know, if you have to imagine the size of this event, I superimpose this event on the place where I'm sitting here, which is the data center. at the University of Wisconsin. And you see the size of this event is like 5 city blocks. So you have a lot of information. And so we can reconstruct the energy like a pretty decent particle detector at Fermilab or CERN. So we looked at the 2 years of data, and we found 26 more of these and published it in 2013 and claimed we had discovered cosmic neutrinos. Now you wonder, this is how we were supposed to discover cosmic neutrinos. Remember, we were supposed to be looking for neutrinos coming through the Earth, and then they would make a muon going through the detector. While we were all trying to find this 26 event, one graduate student was still working on the old idea of Markov. And here is what he found. This is a more modern version. But you just plot the number of muons coming through the Earth, and our detector turns on about 100 GeV, so a tenth of a TeV. And then that's the threshold. Most of the muons we detect from the atmosphere have an energy of about 1 TeV. And then the atmosphere, as I said, it cannot produce efficiently high energy neutrinos. We can measure this flux, and calculate it, and it should follow this blue line. It's a beautiful calibration of the detector. But you see, we discover an excess. And these excess are the neutrinos coming from the cosmos. And when we look at how many we see, it agrees exactly with the ones we detect as electroneutrinos. So this is a confirmation well above 5 sigma of the previous discovery. So now the obvious question that remains is, where do they come from? And then we are finished. First of all, if you look at the sky, this is 1 year of neutrino data. 138,000 points are in the sky. It's totally isotropic. That's not surprise because the atmosphere is isotropic, so that's what we are looking at. And we know now from the measurement we just made, there are actually 200 neutrinos among these 138,000 coming from the cosmos. So let's just look at 12 or so that are separated from the atmospheric background. And we have been doing this for many years by the time I made this picture. And you see the surprising thing is, this map is totally uniform. Where is the galactic plane? We actually don't see the neutrinos nearby. We see the neutrinos from galaxies far away, but we don't see our own galaxy. That was the first surprise. The second surprise is, you see, that's what you're supposed to see by just geometry. If you put sources in galaxies in the universe, you first see your own galaxy. We don't. The other surprise was, this is the light reaching us from the universe in all different forms, different wavelengths. Here is the microwave background, you see, that dominates the light reaching us from the universe, the 411 per cubic centimeter. And then you go through the different wavelengths of light, including visible light, X-rays, gamma rays, and then the universe turns dark. But before it turns dark, it reveals the flux of light in this extreme dark universe. It's just that it's attenuated. But look, this is one of our analyses. There's more energy in neutrinos in the extreme universe than in gamma rays. Nobody expected that. And so that was the second surprising discovery. We confirmed this in other ways, but I won't go through this but just before seeing any neutrino stars, we have already 2 surprises. We don't see our galaxy, And there are more neutrinos, more energy reaches the universe from in neutrinos than in light in this dark universe of cosmic accelerators. So, but we really have to figure out where they come from, and this is where all my slides are new. Let's go back to this. This is hopeless. In fact, if I put 10 years of data there, you don't see anything. And so I'm going to tell you, we discovered sources of neutrinos, and you see here is one source. It's actually a simulation, a computer simulation of the source. The red neutrinos come from the source, and the blue are the background from the atmosphere. Now, if I don't turn this, if I take the color away, this is what it looks like. You don't see anything. So we developed methods to look, which is called maximum likelihood methods, to look for clusters of neutrinos. In other words, more places where more neutrinos reach us than from the uniform background made by the atmosphere. And so what I can do, you're not looking at neutrinos here, you are looking at a map that at each point in the map gives you the probability that there is a neutrino concentration of neutrinos of high energy. And the most likely spot in the sky is this spot. You can see it here, and it falls right on top of an active galaxy, NGC 1068. We published this 2 years ago, didn't claim anything, but it was interesting that we also searched through a list of sources. And again, in that list of sources we searched, this was again the source with the highest probability. In other words, if you look at it this way, these three sources, and this one also, they make the map somewhat asymmetric. And you can see this blue line is for this analysis. If you reach this blue line, let me first tell you what this is. This is again the energy flux reaching us from the universe as a function of angle. Here we look, this is down, we look through the Earth, this is the horizon, and then we lose sensitivity because we look, the muons are the neutrinos are no longer filtered by the Earth. Just look at the blue curves. This is the place you have to reach for a 5 sigma discovery. And you see these 4 sources are close or there. And when this is actually our sensitivity, so they are well above our sensitivity, and the local probability reaches 5 sigma. So, but still, are these still limits, or are these interesting fluctuations, and maybe these are really real sources? So that's the question you have to answer. And how do you, by the way, these sources are all active galaxies. There are, I will get to this picture later, but active galaxies are galaxies which have a black hole in the center. They are cannibalizing the stars, the matter, the hydrogen in their own galaxy. So they eat up their own galaxy in this circulated accretion disk. It's like your bathtub emptying in the black hole. And then somehow the magnetic fields manage to accelerate particles along this beam that's called a jet. And so all these sources are objects like this. And of course, theorists don't need confirmation. They had enough evidence, and they started building models of what we saw. this is the flux we saw from this galaxy, whether it was a fluctuation or not. As I said, they were not discouraged. They could understand this flux. I come back to it later. And the models became more and more sophisticated, and that's where we are now. Except, is this really a real source or not? Here is another picture. You see the black hole, the matter swirling in. And what's interesting is that around this black hole, you build up something called the corona, which is a really dense medium. And so there are lots of opportunities in the picture you are looking at to accelerate protons. And then they have to make their way out in this thick corona at the center. And that gives them the target to produce neutrinos. So this is a Disneyland for producing neutrinos. And we actually now think this is where cosmic rays are accelerated and neutrinos produced. I actually showed you how we were, this slide, how we were going to resolve the problem of answering the question there were fluctuations or not. So we need a better detector, and you can either build a bigger one, which we will do eventually, it's called generation 2, or you improve your own detector. And so we went through a whole program of improvements. In fact, our improvements to the detector never stopped, but this was a major effort. And I won't go through the details of this, but we improved the calibration. We actually calibrated each of the 5,000 plus modules individually, rather than to have a generic calibration, which improved our sensitivity to detecting more light from these neutrinos. Then we used machine learning techniques to reconstruct the direction, which I told you you can see by eye, but that's not good enough, and the energy. Then we improved the point spread function of the telescope. I will tell you what this is in a minute. But we also continuously improved the optics of the ice, which is our detector. And I could talk about the optics of the ice forever. This is we understand ice now with a precision that's really impressive, but we want to go on doing this. And the better we understand the ice, the better our detector is. But the other breakthrough was that we improved the pointing. How do you point with neutrinos? Do the neutrinos really point at your source? And so we have a simulation. We can simulate our experiments end to end. And so this is the resolution of your detector. In other words, we typically see the resolution of our detector is like 0.2 degrees. So if you look at a neutrino coming from this direction, you actually see a distribution of neutrinos corresponding to these data points. And what we did in the past was just approximate this by Gaussian functions. Now we actually carefully determined it from our simulation. And so it means we really know much better what distribution of neutrinos to expect when we point at the source. That's called the point spread function of the telescope. If you have it wrong, you lose sensitivity. It's like, having a telescope and you don't understand the optics of your lens. And so you see, this is a big effect in some cases. Like in this case, the Gaussian approximation tells you that's neutrino distribution, but it's actually this. So I couldn't show you the results last time, but here are the new results. We reanalyzed our 10 years of data. We have all our old data on tapes and disks, depending on the time. And so here is our new sky map. You are looking at the probability that there is a star, a concentration of neutrinos. And you see here this spot, difficult to see by eye, it's 5.2 sigma local probability, it's this blue spot, and you see here it's centered again on NGC 1068. We almost double the number of events. There are 80 neutrinos pointing at the source. And of these 80, many have higher energy, which help the probability, but you cannot see that on this plot. So after taking into account the look elsewhere effect, this probability moves from 5.2 locally to 4.2 global. But you have to realize with the method we have no hidden trials. We know exactly what the magnitude is of our look elsewhere effect. So this is a real probability, a mathematical probability. So I sleep well at night. I don't think this can be fake. Another way of looking at the result is, if I look in the direction of the source and plot the number of the neutrinos as a function of angle, you see here in red, the neutrinos produced in the atmosphere, and in blue, you see the excess in the direction of the source. And this is our 0.2 degree resolution you can kind of see with the enhancement here. And the this angular distribution matches exactly the simulation we made of the observation. Another way of looking at it, here is our original result. You see, we point here at the source, and you see there is where it is. In fact, it just touches the point where you should collect 95% of the events. So this is not that good. But you see, when we improved our calibration of the detector, the spot that we point at NGC moves to the real location, which of course we know from the astronomers. And then when we introduce all the analysis improvements, then you see, instead of this big ellipse, you get this smaller ellipse with the source centered within the 68% circle around your observation. So that's the result we published 2 weeks ago in Science. What happens to this slide? So now I can show you the updated version. Remember, this is the 5 sigma discovery. This is our sensitivity. This is up. This is through the Earth. This is from above. Here is the result. You see NGC is now well above this line. The other sources are TXS 0506 and PKS 1424 plus 240. By the way, what are these things? NGC, TXS, PKS are names of catalogs. And these telephone numbers are where are the coordinates, where in the map these sources reside. So, but the interesting thing is they are all active galaxies with supermassive black holes. And so if we look deeper into our analysis, we see other sources. And an interesting one, I showed you the top 3. The fourth one is NGC 4151. And now it's interesting to do some history. Where have we seen the names of these sources before? Well, in 1943, Carl Seifert published this paper where he shows that the 2 brightest spiral galaxies he observes are NGC 1068 and 4151. So nothing is new under the sun, except it's not a sun, it's neutrinos. And here is another paper. In fact, Silverberg and Shapiro in '82 predicted that this could be NGC 4151-1068 could be neutrino sources. And where did you hear TXS 0506 before? Well, these are slides of my previous talk. We had this real-time network to discover sources. And the way it works is when the detector lights up, normally we reconstruct the flash made by a neutrino in the computing center at the surface. Then the data is sent by satellite to Madison, and in Madison, it's further analyzed and reconstructed and then sent to the collaboration. Now we just take the reconstruction made at the pole, and typically within 30 seconds, we send the direction of that neutrino by Iridium satellite to every astronomer in the world who chooses to pay attention to it. Well, this is what happened in 2017, in September. We discovered this 290 TeV neutrino, very likely to be cosmic, and it pointed at the active galaxy TX 0506, which is the same active galaxy that appeared in our 10-year analysis. And in fact, there was a long series of observations. It was later realized it was actually a TeV emitter, which makes it much more likely that this is an accident. At some point, more than 20 telescopes looked at this source. But interestingly, one of them, an optical telescope, looked at this source 73 seconds after we sent the alert. So they were the first to look. Later it was looked at by Swift. Here is the MAGIC satellite, here is Fermi. And the other satellites were trying to look what a host galaxy was and determining the coordinates, the distance. And we looked, if you look at the publication in Science, don't forget to read the second paper, knowing where to look. We looked through our old data, to the 10-year data, and you see this source, the neutrino data are in orange. You see this source, this basically nothing, except for a huge burst in 2014, and then this burst here, which is what I actually have been talking about. And so even though this source emits most of its light in one 100-day burst, even if you average these neutrinos over 10 years, it's still the second source in the sky. And even though it's really far away. So this source is, to theorists, still a puzzle, unlike the NGC 1068. In fact, let me skip this. So what's the conclusion? Where do cosmic rays and neutrinos come from? Well, the inevitable NASA picture, they come somewhere deep from the core of an active galaxy. Whereas I said, you have many opportunities, particles are falling into the black hole, you have many opportunities to accelerate them. You could accelerate them on the accretion disk. And then you have this corona, this optically thick medium that the protons can interact with before they leave the star and make neutrinos, leave the galaxy and make neutrinos. So have we solved the cosmic ray problem? I wish we did, but you know, this is a handful of sources. Are these the only sources? Do other things in the universe make neutrinos? We haven't answered these questions. And as usual in science, when you begin to find answers, the answers raise more questions, and the question raised are more difficult to answer. So the story is definitely to be continued. But what I want you to conclude from this talk is that it looks like we have the tools to solve the cosmic ray problem. Cosmic rays were discovered in 2011 by this man who went to 17,000 feet to see the flux increasing when he rose in his balloon. And so this is more than 100 years ago, and I think it's time to solve this problem, and we'll do our best. Thank you for your attention, and I don't want to stop before pointing out that the young people you see in this plot are the ones who did all the work. Thank you very much.
Thank you, Francis. Thank you very much for your speech about recent results of IceCube. Some metrics, you got an audience of about 300 people around the world.
Wow. And this after the football game.
Yeah. And
thank you.
Greetings for many places around the world also, especially from Mexico and the rest of Latin America.
I have a lot of friends in Latin America. In fact, I had very close collaborators in Latin America during my career as a theorist.
Do you want to take a couple questions?
Yes, as many as you want.
I think a couple questions will be enough.
You decide.
There is an upper limit. This is the questions for the audience. There is an upper limit in the energy of cosmic neutrinos?
Well, I don't know. You have to realize we know the answer now. So that's it. We know how many neutrinos and with what energies reach us from this dark universe. And so we know the answer. But if you had asked me this question before we built IceCube, I would have said we don't know. In fact, there was an upper limit that assumed that the energy would be similar to the one in photons. And I told you already, that's obviously not an upper limit. We saw neutrinos with a higher flux than the one that was claimed to be an upper limit. But that is because the sources, this was based on the energy of photons, and the photons are absorbed and don't come out of these active galaxies. And that's why we see more neutrinos than photons. But now we have answered the question. We know what the energy in neutrinos in the universe is.
Thank you. From the audience is asking if IceCube is looking for magnetic monopoles as well.
We are looking for everything we can think of. And yeah, we have looked at magnetic monopoles. In fact, we have, we typically have the best limits. Everybody looks for magnetic monopoles because we have the biggest detector. And but our limits are already below the Parker bound, well below the Parker bound. And the Parker bound is an upper limit on the flux of monopoles, which is set by the fact that if there were more monopoles, they would destroy the magnetic field of our galaxy, which is something that's not happening. So, yeah, we are still doing this, just like we are still looking for dark matter in the sun and elsewhere, and haven't found it yet. But we keep going.
Thank you. Another question for the audience is that you can distinguish using IceCube detector between neutrinos and antineutrinos.
The answer is no, but no is a qualification. In fact, I think I talked about this the last time. I'm rather sure. So we have no magnetic field. And so we look at a muon made by a neutrino and an antineutrino, and they have different charge. If you can tell the charge of the muon, you can tell a neutrino from an antineutrino. But we have no magnetic field. The Earth magnetic field is not strong enough to separate them. But there is one way I talked about the last time. With an antineutrino, you can actually, unlike, there is one case, I've consistently told you during this lecture that neutrinos, they don't interact with atoms. They only interact with the nuclei. That's why they interact so weakly, and where they can reach us from the whole universe. But there is an exception to this. That is when an anti-electron neutrino interacts with an electron, an atomic electron, and makes a weak intermediate boson of ATF, the W. And we actually detected one event. It's called the Glashow resonance event. And we detected this W. And so we know it comes with the, the laboratory equivalent energy of producing an ATF particle. So that neutrino had an energy of 6,300 TeV. And that's exactly the energy you need for an anti-electron colliding with an electron to make a W. And so we know that event was an antineutrino, but that's the only one. For all the other ones, we are in the dark. But when we get more of these events, we hopefully can eventually begin to reconstruct. We need a bigger detector. And we have already designed it, and it has been endorsed by the Decadal Review of Astronomy of the Academy of Science. So we'll see what happens. But then we will be able to measure how many neutrinos and antineutrinos there are in our beam.
Thank you. The question is for Carlos Garcia. If you want to say some words about this presentation?
Oh, yes, of course. I would like to congratulate Francis for his very nice talk. And I learned a lot, even if I have been interested in IceCube for a long time. And let me ask a question related with your last sentence. How is the status of the upgrade of IceCube?
Yeah, we actually, of course, we were delayed by COVID, not for the science. As I said, the detector is purely digital. And so the data keeps coming. It's like a satellite, basically. There are two people at the pole watching if something goes wrong, but normally they have nothing to do. And that's often the case, actually. But so during COVID, there was no activities, I mean, major activities. People could go in and out of the pole, but you couldn't build things. So now we will upgrade IceCube in the Antarctic summer 2025-26. We'll put in 7 more strings, but this is mostly to do particle physics measurements, which I didn't talk about, to do neutrino oscillation measurements. There's much more I didn't talk about than what I talk about, you must realize. And then we want, after that season, we would like to start reconstructing the next generation detector. We have a design, and as I said, we submitted the design for review to the Decadal Review of Astronomy, and they endorsed it, which is actually, it made me really feel good, because if you look at that picture that I think is still on the screen, these people are all physicists with, 1 or 2 exceptions. And you know, I never thought I would see the day that we would be, you know, supported by the astronomy community. And so that's a really big reward for us.
Right. And I have another question related with the possibility of compare your excess in directions from which the neutrino are coming with the anisotropy that Auger claims that they find with the in general cosmic rays.
I think everything Auger claims, I think, is consistent. I don't, first of all, there are no contradictions.
Fine.
As you know, Auger is very careful in his claims. So
yes.
You also have to realize that doing multi-messenger astronomy is not simple.
No.
Because, as I explained, the sources like the active galaxies, they make neutrinos, they don't make gamma rays.
Mm-hmm.
Gamma rays are absorbed and come out as X-rays, actually. So if you look at gamma rays, you will see different sources as when you see neutrino sources. And where the protons lose a lot of energy in the target to make neutrinos, they will come out at lower energy. So there's not necessarily a correlation between proton sources and neutrino sources. I think they are the same sources, but the individual objects, they may see actually different active galaxies than we see, but they would be all in the same category. Eventually, we could understand them as one, you know, as one model of the accelerator. So multi-messenger astronomy is subtle.
Yeah, I imagine. Thank you, Francine. I hope the best for you. Bye-bye.
Thank you. It was a pleasure. Bye.
Thank you. Thanks, Carol. More metrics. People is following you from Twitter, Instagram, YouTube, and Facebook at the same time, all around the world. Do you want to offer some closing remarks for your audience?
Sorry, are you still talking to me?
Yes, if you want to offer some closing remarks for your audience.
No, you know, it's a pleasure. I have now given this lecture twice. And in fact, I received several emails after my first lecture, which I was happy to answer. I think I even had a Zoom call with someone who listened to the first lecture. So please contact me again. It's easy to remember, Halzen at icecube.wisc.edu, or look up, type IceCube in Google, and you will eventually find my address. So if you have more questions you think about, please contact me.
Okay, thank you.